Welcome to Nimo's World. It's me Nimesh Naik. Today I am discussing CSIR net questions June 2011. Topic complex analysis. So first question, it's a part B question. Let f from C to C be a complex valued function given by f of z is equal to u of x comma y plus I into v of x comma y. Suppose that v of x comma y is equal to 3xy square. Then option number 1, f cannot be holomorphic on C for any choice of u. And option number 2, f is holomorphic on C for a suitable choice of u. And option number 3, f is holomorphic on C for all choices of u. And option number 4, v is not differentiable as a function of x comma y. So in this question we have given that f from C to C be a complex valued function and f can be represented as f of z is equal to u plus iv, and we have given that v is equal to 3xy square. So we want to check whether f is holomorphic for a suitable choice of u or not. So first of all we want know some note. So note number 1, analytic functions are called holomorphic. That is, holomorphic means analytic. Holomorphic functions means analytic functions. Now this question is solved by using a theorem. So I just state that theorem. Let f from D to C be a function where D is a domain in C. Domain means open connected set. Then let f be analytic and let f of z is equal to u plus iv. Then u and v are harmonic in D. That is, u xx plus u yy is equal to 0 and v xx plus v yy is equal to 0. That is, u and v are harmonic in D. That means u and v are satisfying the Laplace equation. So ux xx plus uyy is equal to 0 means u satisfying the Laplace equation. U satisfying Laplace equation means that u is harmonic in our domain. Okay, now we are going to our question. From the question we have given that v of x comma y is equal to 3xy square. So we are differentiating v with respect to x. So vx is equal to 3y square and differentiating v with respect to y. So we get vy which is equal to 6xy, and we are differentiating vx with respect to x. So vxx which is equal to 0, and similarly vyy is equal to 6x. So we have vxx plus vyy which is not is equal to 0. That is, vxx is equal to 0 plus vyy here which is equal to 6x. So we get 0 plus 6x which is equal to 6x. That is, we can say that vxx plus vyy not is equal to 0 except at 0, 0. That means v does not satisfy our Laplace equation. V does not satisfy our Laplace equation means that v is not holomorphic. V is not harmonic. So v is not harmonic implies that f cannot be holomorphic on C for any choice of u. Because we have the theorem f is holomorphic, then u and v are satisfying the harmonic equation. U and v are harmonic. That is, u and v are satisfying the Laplace equation. So here we can get v is not harmonic. V is not harmonic means that f cannot be holomorphic on C for any choice of u. Now we are going through our options. Our first option which says that f cannot be holomorphic on C for any choice of u. So we have get f cannot be holomorphic on C for any choice of u, and our first option is the same condition. So our first option is correct option, and our second option says that f is holomorphic on C for a suitable choice of u, which is a false statement because we can get f cannot be holomorphic on C for any choice of u. And third option, f is holomorphic on C for all choices of u, which is also a wrong statement. And also we know that v is equal to 3xy square is differentiable. So our fourth option, which says that v is not differentiable as a function of x and y, which is a false statement because v is differentiable. Therefore our fourth option is also wrong. So the correct option of this question is option number 1. Okay. Next question, it's also a part B question. The power series summation n ranging from 0 to infinity 2 power minus n into z power 2n converges if option number 1 mod z less than or equal to 2, and option number 2 mod z less than 2, and option number 3 mod z less than or equal to root 2, and option number 4 mod z less than root 2. So for solving this question, first of all we want to know what is radius of convergence. So the definition of radius of convergence: consider the power series summation n ranging from 0 to infinity an into z minus z naught all power m. Let r be the radius of convergence, then r is equal to 1 by limit supremum mod an all power 1 by n. Okay, so this is our equation to find the radius of convergence. So r is equal to 1 by limit supremum mod an all power 1 by n. This equation is can be used only if limit supremum mod an power 1 by n is exist. Otherwise we cannot use this equation. Now we are going to our question. We have summation n ranging from 0 to infinity 2 power minus n into z power 2n. So here we can given that a to n. So this is a to n because z is of power 2 power n. So here a to n, which is equal to 2 power minus n, then limit supremum mod a to n all power 1 by 2n, which is equal to limit supremum mod a to n is equal to 2 raised to minus n, so which become limit supremum mod 2 power minus n all power 1 by 2n, so which is equal to limit supremum mod 2 power minus 1 by 2, which is equal to limit supremum 1 by root 2, which is equal to 1 by root 2. That is, we get limit supremum modulus of a to 2n all power 1 by 2n, which is equal to 1 by root 2. That is, limit supremum exists. Therefore we can r is equal to 1 by limit supremum mod an all power 1 by n, so which is equal to 1 by the value of limit supremum, which is equal to 1 by root 2. So here substituting we get 1 by root 2, which is equal to root 2. So we have get the radius of convergence of this power series r is equal to root 2. That is, we can say that the given power series converge inside mod z less than root 2. That is, we get the radius of convergence r is equal to root 2. Then we can say the given power series converge inside mod z less than root 2. Now we want to check whether this series is converge or diverge at the point root 2. So for that, at the point root 2, we are computing summation 2 raised to minus n into z power 2n, which is equal to summation 2 power minus n into root 2 all power 2n. So which is equal to summation 2 power minus n into 2 power 1 by 2 all power 2n. So which is equal to summation 2 power minus n into 2 power m. Which become 2 power minus n plus n, which is equal to summation 2 power 0, which is equal to summation 1. And we know that summation 1 is diverges. Therefore at root 2 the power series is diverges. We can get it. We are checking at the point root 2 the given power series is converges or not. So we can get at root 2 the power series is diverges. Therefore we can say that the power series summation n ranging from 0 to infinity 2 raised to minus n summation 2 power n converges if mod z less than root 2. Now we are going to our options. Our first option, which says that the given power series is converges when mod z less than or equal to 2. So which is false because we can get mod z less than root 2, the given power series is convergent. And second option which says that mod z less than 2, which is also wrong. And third option which says that mod z which is less than or equal to root 2, which is false, because at root 2 our given power series is diverges. Therefore our fourth option which says that mod z less than root 2, so which is a correct option of this question. So here we are using the definition R is equal to 1 by limit supremum of mod a n all power 1 by n. So which is used only when limit supremum of mod a n all power 1 by n is exist. So here we can get the power series which converges if mod z less than root 2. Therefore our correct option of this question is mod z less than root 2. Okay. Now next question, it's a part C question. Let f from d to d be a holomorphic with f of 0 is equal to 1 by 2 and f of 1 by 2 is equal to 0, where d is equal to set of all set such that mod z less than or equal to 1, then which of the following is correct? Then option number 1, mod f dash of 0 which is less than or equal to 3 by 4, and option number 2, mod f dash of 1 by 2 which is less than or equal to 4 by 3, and option number 3, mod f dash of 0 which is less than or equal to 3 by 4, and mod f dash of 1 by 2 which is less than or equal to 4 by 3, and option number 4, f of z is equal to z for r z belongs to d. So we have given that f from d to d be a holomorphic function with which is satisfying the condition f of 0 is equal to 1 by 2 and f of 1 by 2 is equal to 0. And we have given that d is equal to set of all z such that mod z less than or equal to 1. Now we want to pick the correct statement from these options. So this question is just an application of short-pick lemma. So we have to know what is short-pick lemma. So just I state that lemma. So short-pick lemma statement. Let f be analytic in the open disk. D is equal to set of all z belongs to C such that mod z less than 1, and let mod f of z which is less than 1 for all z belongs to D. If f of a is equal to b for some a comma b belongs to D, then mod f dash of a which is less than or equal to 1 minus mod b or b square divided by 1 minus mod a square. That is mod f dash of a which is less than or equal to 1 minus mod f of a whole square divided by 1 by mod a whole square. Okay, so that is our statement of short-pick lemma. Now we are going to our question. We have given that f from d to d be holomorphic function. Holomorphic function means that analytic function, and also given the condition f of 0 is equal to 1 by 2 and f of 1 by 2 is equal to 0. So we are applying short-pick lemma. By using short-pick lemma, we have mod f dash of a which is less than or equal to 1 minus mod f of a whole square divided by 1 minus mod a square. By using this, we can easily compute mod f dash of 0 and mod f dash of 1 by 2. Therefore, mod f dash of 0 which is less than or equal to 1 minus mod f of 0 whole square divided by 1 minus mod 0 square. And we have given that f of 0 is equal to 1 by 2. So which is equal to 1 minus mod 1 by 2 whole square whole divided by 1 minus 0, which is equal to 1 minus 1 by 4 whole divided by 1, so which is equal to 3 by 4. That is, we have get mod f dash of 0 which is less than or equal to 3 by 4. That is mod f dash of 0 which is less than or equal to 3 by 4. Because we have given that f of 0 is equal to 1 by 2. So by using by using short-pick lemma, we can say that mod f dash of 0 which is less than or equal to 1 minus mod f of 0 whole square divided by 1 minus 0 square. So by using this, we can get f dash of 0 is equal to f dash of 0 which is less than or equal to 3 by 4. Similarly, we can calculate mod f dash of 1 by 2 because we have given that f of 1 by 2 which is equal to 0. So by short Pick lemma, we have mod f dash of 1 by 2 which is less than or equal to 1 minus mod f of 1 by 2 all square whole divided by 1 minus mod 1 by 2 all square. So which is equal to 1 minus 0 square, because f of 1 by 2 is equal to 0. So which is equal to 1 minus 0 square whole divided by 1 minus 1 by 4. So which is equal to 1 by 3 by 4 which is equal to 4 by 3. That is, we can get mod f dash of 1 by 2 which is less than or equal to 4 by 3. Okay, so we can get a mod f dash of 0 which is less than or equal to 3 by 4 and f dash of 1 by 2 which is less than or equal to 4 by 3. Now we are going through our options. Okay, our first option which says that f dash of 0 which is less than or equal to 3 by 4 which is a correct statement, because we get f dash of 0 which is less than or equal to 3 by 4. And our second option which says that mod f dash of 1 by 2 which is less than or equal to 4 by 3, and which is also true because we get f dash of 1 by 2 which is less than or equal to 4 by 3. Therefore our first option is correct and second option is correct. Now our third option which says that mod f dash of 0 which is less than or equal to 3 by 4 and mod f dash of 1 by 2 which is less than or equal to 4 by 3, because we have get f dash of 0 which is less than or equal to 3 by 4 and f dash of mod f dash of 1 by 2 which is less than or equal to 4 by 3. Therefore our third option is also correct. Now our fourth option is saying that f of z is equal to z for all z belongs to D. So if we have given that f of 0 is equal to 1 by 2. If we are suppose that f of z is equal to z is true, then f of z is equal to z implies that f of 0 is equal to 0. But we have given that f of 0 is equal to 1 by 2. So if f of z is equal to z, which contradict the given condition, f of 0 is equal to 1 by 2. Therefore our fourth option which says that f of z is equal to z for z belongs to D, which is a wrong statement. So our fourth option is wrong. So the correct option of this question is 1, 2 and 3. Okay, since it is a part B question, since it is a part C question, multiple answers are correct. So the correct option of this question is option number 1, option number 2 and option number 3. Okay, now next question, it's also a part C question. At z is equal to 0, the function f of z is equal to e power z plus 1 divided by e power z minus 1 has option number 1 a removable singularity, and option number 2 a pole, and option number 3 an essential singularity, and option number 4 a residue of f of z at z is equal to 0 is 2. So we have given that f of z is equal to e power z plus 1 divided by e power z minus 1, and also given that z is equal to 0 is an isolated singularity. Now we want to check whether it is a removable singularity or it is a pole or an essential singularity, and also we want to compute the residue of f of z, that is this function at z is equal to 0. So first of all we want to know what is removable singularity and what is pole and essential singularity. So we are going through the definitions. So first of all the definition of removable singularity. So definition: an isolated singularity z not belongs to C of f is a removable singularity of f if limit z tending to z not f of z exists finitely. That is, a point z not belongs to C is said to be a removable singularity of a given function if limit z tending to 0 f of z exists finitely. That is, limit z tending to z not f of z which is strictly less than infinity. Now we want to know the definition of pole, which says that a isolated singularity z not belongs to C of f is a pole of f if limit z tending to z not f of z is equal to infinity. That is, we are computing limit z tending to z not f of z and we have get which is equal to infinity. Then we say that z not belongs to C is a isolated singularity of f. Now we want to know the essential singularity definition. An isolated singularity z not belongs to C of f is an essential singularity of f if limit z tending to z not f of z does not exist. That is, limit z tending to z not f of z does not exist finitely and it cannot be infinite. Okay. Next we want to know a knot. So knot, if Z naught is a simple pole of f of z, then residue of z is equal to z naught, f of z is equal to limit z tending to z naught, z minus z naught, f of z. That is, z naught is a simple pole, then we can compute using like this. If it is z naught is a simple pole only, then residue of z is equal to z naught, f of z is equal to limit z tending to z naught, z minus z naught into f of z. Now we are going to our question. We have given that f of z is equal to e power z plus 1 divided by e power z minus 1, and 0 is an isolated singularity of f, because at a 0 f of 0 is equal to e power 0 plus 1 divided by e power 0 minus 1, so which is equal to 1 plus 1 divided by 1 minus 1, so 2 by 0, therefore which is not defined, so we can say that 0 is an isolated singularity of f. Now we want to check whether this 0 is a removable singularity, or it is a pole or essential singularity. For that we are computing limit z tending to 0 f of z, which is equal to limit z tending to 0 e power z plus 1 divided by e power z minus 1, so which is equal to infinity. Therefore we can say that 0 is a pole of f of z. So we have get 0 is an isolated singularity of f, and 0 is a pole of f of z. Now we want to check also limit z tending to 0, z minus 0 into f of z, which is equal to limit z tending to 0 z into f of z, which is equal to limit z tending to 0 z into e power z plus 1 divided by e power z minus 1. When we apply the limit, z is equal to 0, so 0 into e power 0 plus 1 divided by e power 0 minus 1, so 0 divided by e power 0 1 minus 1, which is equal to 0, so we get 0 by 0 form. Therefore we are applying L'Hopital rule, therefore we are differentiating the numerator and the denominator separately, then which is equal to limit z tending to 0 z into e power z plus e power z plus 1 divided by e power z. Then we apply the limit, z is equal to 0, then we get z 0 into e power 0, so which is become 0, and e power 0 plus 1, so 1 plus 1, which is equal to 2 divided by e power 0 1, so which is equal to 0 plus 2 divided by 1, which is equal to 2, which is not is equal to 0. Therefore we can say that 0 is a simple pole of f of z. So we have get 0 is an isolated singularity, and it is also a pole of f of z, and 0 is a simple pole of f of z. Since 0 is a simple pole, we for calculating the residue of f of z at z is equal to 0, we can use the above note. So by above note we can residue of z is equal to 0 f of z, which is equal to limit z tending to 0 z minus 0 f of z, so which is equal to 2. Therefore we can get, because this we can already computing here this, so we are directly saying that which is equal to 2. So we have get a residue of z is equal to 0 f of z is equal to 2, and 0 is a pole of f of z. Now we are going to our options. Now our first option, a removable singularity, which is false, and a pole which is correct, and third is an essential singularity, which is false, and the residue of f of z at z is equal to 0 is 2, which is also 2, because we have get z is equal to 0 is a pole, and residue of f of z at z is equal to 0 is 2. So the correct option of this question is option number 2 and option number 4, and the remaining options are wrong. Okay. Next question, it's also a part C question. Define h plus is equal to set of z belongs to C such that y greater than 0, and h minus is equal to set of z belongs to C such that y less than 0, and L plus, which is equal to set of z belongs to C such that x greater than 0, and L minus is equal to set of z belongs to C such that x less than 0. Then the function f of z is equal to z by 3z plus 1 Option number 1 maps H plus onto H plus and H minus onto H minus, and option number 2 maps H plus onto H plus and H minus onto H plus, and option 3 maps H plus onto L plus and H minus onto L minus, and fourth option maps H plus onto L minus and H minus onto L plus. So we have given that H plus, that is the upper half plane and lower half plane, left half plane and right half plane. Then we want to check whether the function f of z is equal to z by 3z plus 1 and which of the following are correct. So we want to know a knot. By using that knot we can simply solve this question. So that knot: the general form of a bilinear transformation which maps real line to real line is T of z is equal to az plus b divided by cz plus d, where ad minus bc, which is not is equal to 0, a comma b comma c comma d belongs to R. That is, the general form of a bilinear transformation which maps real line to real line is T of z is equal to az plus b divided by cz plus d, and ad minus bc, which is not is equal to 0. Ad minus bc, which is not is equal to 0, means that ad minus bc, which is greater than 0, or ad minus bc, which is less than 0. And note number 2, if AD minus BC greater than 0, then T maps the upper half plane, that is H plus, onto itself, and the lower half plane H minus onto itself. That is, if AD minus BC greater than 0, then T maps upper half plane to upper half plane and lower half plane to lower half plane. So we have given that f of z is equal to z divided by 3z plus 1. So which is the form of a bilinear transformation. So we can use this result here. So here we have f of z is equal to z divided by 3z plus 1. Here the term b is equal to 0. So from this we can computing AD minus BC. So here A is equal to 1 and D is equal to 1 and B is equal to 0 and C is equal to 3. So computing AD minus BC, which is equal to 1 into 1 minus 3 into 0, so which is equal to 1, and we know that 1 greater than 0, therefore we have get AD minus BC, which is equal to 1, which is greater than 0. Then we can, by using the note, we can say that f maps H plus to H plus and H minus to H minus. Okay, so that is, we have f of z is equal to z divided by 3z plus 1, which is a bilinear transform, which is of the form of a bilinear transformation which maps real line to real line. So for that bilinear transformation we have a note AD minus BC, which is greater than 0, then if that bilinear transformation maps upper half plane to upper half plane and lower half plane to lower half plane. So by computing AD minus BC we get which is equal to 1 and which is greater than 0. Therefore we can say that upper half plane, that is H plus, maps to H plus, and lower half plane, that is H minus to H minus. Lower half plane maps to lower half plane. So more clearly consider H plus, which is equal to set of all z belongs to C, such that y greater than 0. That is, y greater than 0 means if we are considering the plane, then set of all z belongs to C such that y greater than 0 means that this portion. So above the region above the x-axis. So H plus is equal to set of all z belongs to C such that y greater than 0, which is a upper half plane. Now we are choosing a point in the upper half plane. We are choosing a point which is from the upper half plane. So we know that I belongs to H plus, because if we are considering the complex plane, so if we z is equal to x plus iy, then this coordinate varies from for x and the I coordinate varying for y axis. So I means here the y point, so here. So we have said that I belongs to H plus. Now we are calculating the F image of I. Then we are checking whether this F image lies in which plane. So we are computing f of I. F of I means if we have f of z is equal to we have f of z is equal to z divided by 3z plus 1. So we are substituting I instead of z. So we get f of z is f of I is equal to I divided by 3i plus 1, which is equal, then we are conjugate multiply, which is equal to I by 3i plus 1 into minus 3i plus 1 divided by minus 3i plus 1. When we multiply I into minus 3i, which become 3 minus 3 into minus 1, because I square is equal to minus 1, so become plus 3, and 1 into I, so which is equal to 3 plus I, and 3i plus 1 into minus 3i plus 1, which is equal to 3 square plus 1 square, which is equal to 9 plus 1, which is equal to 10. So we get which become 3 by 10 plus 1 by 10 I. So we have get f of I, which is equal to 3 by 10 plus 1 by 10 I, and we know that this is our imaginary part. So 1 by 10, which is greater than y greater than 0, so which is lies in the upper half plane. So this complex number which is lies in the h plus upper half plane, therefore we can say that f of I lies in the upper half plane. That is, if we are choosing a point in the upper half plane, then f image of that point must be lie in the upper half plane. Therefore we can say that f maps h plus to h plus. Similarly, we can if by considering the lower half plane means set of all z belongs to C such that y less than 0, that is if we are considering which goes to x axis and it become y axis. So y less than 0 means that the region below the x axis. So similarly, if we are taking a point minus I, and if you calculating f of minus I, that point must be belong in the lower half plane. That is an exercise for you. If you are doing, then you get f of I lies in the lower half plane. Therefore similarly we can say that f maps h minus onto h plus. So from these options we have get our first option is correct option, because which says that f maps h plus to h plus and h minus to h minus. So our first option is correct option, and the remaining options are false. Okay, so the correct option of this question is option number 1. Okay, thank you. If you like my video, please subscribe my channel and also share and like.